This talk covers basic issues related to WRF verification. WRF has been applied in operational forecast of weather and climate. We need to monitor the forecast quality and get ideas how accurate the forecast is. This is why many weather service centers conduct daily verification and evaluate the model performance. In the research field, WRF has been applied for studies of almost all the physical and dynamical processes in the atmosphere. With so many physics options available in WRF, how can we know which schemes should be used for the case and region we are concerned? The model verification can give us the answer. More important, the evaluation of model performance will help us to identify possible problems. Such kind of information is important for us to further improve the physics and dynamics of the modeling system. Before we start to look at the verification, I would like to present an example of WRF-based model verification results. This is a good example to demonstrate how verification can help us to find possible problems in the model. This is an example of verification based on HER. HER is the high-resolution rapid refresh modeling system used by NOAA. It is based on WRF LRW. This system has been applied for real-time weather forecast at 3-kilometer resolution in the past several years. At this resolution, it is cloud resolving and convection allowing. Forecasts of HER over a 3-week period in the summer of 2010 are verified with a focus on precipitation. This slide shows the model domain. Precipitation forecasts in 2 subregions, the upper Midwest and the southeast U.S., are verified against observations. This is the diurnal cycle of storm numbers. The left is for the upper Midwest and the right for the southeast. The solid and the dotted lines are for simulations and observations respectively. What can we find in this plot? In the upper Midwest, observations and model simulations have a similar diurnal cycle. This means that there is no apparent timing error in the storm initiation and development. In the southeast, however, the model produced a much smaller number of storms. The time for the storm number to increase is also late. This result indicates that the initiation of new storms is later than observations. It also indicates that the model underestimated the development of new storms. This slide displays the total number of storms as a function of the storm size. The left column is for the upper Midwest, the right is for the southeast. Black and gray columns are for simulations and observations respectively. From the top to the bottom are forecasts at different lead time. The point I want to make here is that for both the upper Midwest and the southeast, the model has trouble to maintain large storms. In other words, it can produce large systems for short forecast lead time, but for longer lead time, the number of large storms in the forecast is much smaller than observations. What can we learn from the verification results? What is the physics behind such a result? Storms in the upper Midwest are dominated by synoptic scale forcing, which often leads to large and organized precipitation systems. In the southeast, however, storms are often scattered and isolated because they are driven by local diurnal heating. Model description of such kind of physics still need to improve. We also need to figure out why the model failed to maintain large-size storms in its simulation. This is a good example what we can learn from the verification. Now let's take a look at WRF verification. This talk will include the following topics. First, I will introduce some basic knowledge and methods for the verification of WRF simulation. I will focus on traditional metrics, but will also introduce new methods for more detailed verification. I will give examples for these methods. By the way, NCAR provides a complete verification package, the model evaluation tools. We call it MAT. We can find all the information in the MAT user's website. If we are interested in verification, then MAT will be a very useful package. For the verification of WRF simulations, we focus on two types of forecast variables, the continuous variables and the categorical variables. Continuous variables have values from WRF simulations and also from observations. Temperature, precipitation, wind speed, and wind direction are typical continuous variables. Categorical variables usually refer to the occurrence of a specific event. For example, precipitation versus no precipitation, strong winds versus no winds, fogs versus no fogs, etc. These are typical categorical variables. Verification of continuous and categorical variables are different. Let's first look at the verification of continuous variables. Three most commonly used measures for continuous variables are the mean error, mean absolute error, and root mean square error. The mean error is the average of all the differences between simulations and observations. Positive values indicate the forecast is too high on average, and the negative values indicate the forecast is too low. However, the mean error doesn't give us any indication of the magnitude of the errors. It is possible that the mean error could be zero, but the forecast could have large bias because positive and negative errors can offset each other. The mean absolute error measures the average magnitude of the forecast error, but it doesn't consider the direction. It measures the accuracy of the forecast. The root mean square error also measures the average magnitude of the forecast errors, but it gives high weight to large errors. This means that the root mean square error is most useful when large errors are specifically concerned. Scatterplot is a simple but useful method for the verification of continuous variables. Here is an example. Suppose this is a scatter plot for temperature forecast. The forecast is on the horizontal axis, and the observation is on the vertical axis. If the forecast is perfect, then the forecast and observation values should be represented by the diagonal at 45 degrees. In this figure, all the points above the diagonal indicate they are forecast too cold, and those below the diagonal are forecast too high. If we want to answer some specific questions, for example, can we say all the forecast is too low for temperature above 10 degrees? Is it true that all the observed temperature below negative 20 degrees are forecast too high? This figure will tell us the answers. Scatterplot can also tell us whether the forecasts and the observations are linearly correlated. That is, large observation values should always correspond to large forecast values. The two scatter plots shown here represent two different sets of forecasts. The observations are the same. In both cases, lower forecast temperature values tend to be associated with lower observed temperatures. However, note that for the left panel, the correlation might be very high, indicating that the forecast is well correlated with observations. For the right panel, we may also get a positive correlation between the observations and the forecast, but the correlation is low and the result doesn't really make sense. Evaluation of model-generated vertical profiles is also one important aspect of the model verification. Profiles of meteorological variables can be extracted from the WRF output files and placed on the designed location and time. We have options to use a sounding from the grid point nearest to the designed location. We can also horizontally interpolate WRF to the designed location. WRF post-process allows for vertical interpolation of model results to either pressure levels or height levels. As a general rule, the interval of pressure levels should not be too large. For example, it is better not larger than about 50 millibar. For the interval of vertical height levels, the layers can be very thin for close examination, yet they are allowed to be thinner for regions of less detailed study. One can select layers of 5 or 10 meters near the top of the boundary layer, and perhaps 500 meters in the upper troposphere. It is better to verify model results against in-situ observations. This is because errors might be introduced into the analysis and reanalysis products because of the assimilation. Here I list some websites where we can download the sounding data. One is the weather website of the University of Wyoming. It provides WMO soundings in several formats, including the text format. The other website is maintained by NOAA. It also provides WMO soundings. Many weather service centers provide daily verification products on their website. Here I list the websites of NSAP and ECMWF. Verification of ensemble forecast can be found in Japan Weather Agency. If we are interested in this topic, we can take a look at these websites and get some useful information. This is an example of sounding data download from University of Wyoming weather website. It is straightforward and easy to process. Station observations can be found in the NSAP GDAS data. The GDAS data in pre-BARF format provides global surface and upper air observations. The website to download the GDAS data and the user guide for processing pre-BARF format data are listed here. This is an example of vertical profile verification. 40 cases of WRF run are verified against the soundings. The solid lines show the mean errors with different PBL schemes. The dashed lines show the root mean square error. This slide tells clearly the cold or warm bias in the different levels. Since the difference between the mean error and the root mean square error is not large, we can say that very large errors are unlikely to occur. This slide displays the verification of model simulation against the station observations. It shows the spatial distribution of model errors. Such kind of information gives us a first guess what could be the possible reason for the bias. For example, this figure shows that surface temperature has a cold bias over the high elevation region of West US. This is a common feature in WRF simulation when using NOAA land surface scheme. It is possibly related to the poor representation of snow physics in NOAA. We have discussed the verification of continuous variables. Now let's take a look at the categorical variables. A categorical forecast is a forecast of the occurrence or non-occurrence of a specific event, which must be clearly defined. Categorical variables often involve in the yes or no forecast. To verify this type of forecast, we often start with a contingency table that shows the frequency of yes and no. Several commonly used measures can be derived from the contingency table. I list a few of the metrics that are commonly used here. Typically, the forecast is evaluated using a diagram like the one shown in this figure. In this diagram, the area H represents the intersection between the forecast and observations, where the forecast is correct. M represents the observation that was missed by the forecast. F is the forecast that is never observed. This is the false alarm. A false area is the area outside both the forecast and observation, which is often called the correct rejections. The above situation can be represented in a contingency table. Suppose we are making precipitation forecast. Following the forecast of yes or no, precipitation will actually occur or not occur. This leads to 4 possibilities laid out in the table. In this table, the entries in each cell represent the counts of correct forecast, misses, false alarms, and correct rejection. The counts in this table can be used to compute a variety of traditional verification metrics. Some commonly used metrics for verification. The accuracy tells what fraction of the forecast is correct. The threat score answers the question how well the forecast yes events correspond to the observed yes event. Bias measures the ratio of the frequency of forecast event to the frequency of the observed event. Some other important metrics. The probability of detection tells us the fraction of the observed yes events that are correctly forecast. False alarm ratio is the fraction of the predicted yes events that actually did not occur. False alarm rate is the fraction of the observed no events that are incorrectly forecast as yes events. This is an example to calculate metrics using contingency table. Suppose daily rain forecast and observations over 1 year period produced this contingency table. Categorical statistics that can be computed from the yes or no contingency table are given below. The accuracy is 0.38, indicating that 38% of all forecasts are correct. Bias is 1.14. It means that the rain frequency is slightly over forecast. Probability of detection is 0.78. This tells us that 78% of the observed events are correctly predicted. False alarm ratio is 0.32, indicating that 32% of the forecast rain events are not observed. The bottom two are threat score and equitable threat score. Note that ETS is lower than TS. This is because ETS is adjusted for correct forecast associated with random chance. It is always easier to forecast a rain event in a wet climate than in a dry climate. Now let's take a look at some problems in traditional verification methods. One big issue in the traditional metrics is that they are scale dependent. We know that it is easy to predict precipitation over a large area, but it is not that easy to predict precipitation in a small area with many details. For warm season precipitation, which is often driven by local heating and characterized by scattered and isolated convective storms, it is hard to predict since such kind of storms have many small-scale details. With the ever-increasing resolution of the numerical models, forecast of precipitation with small-scale details is becoming practical. The double penalty issue, as illustrated by this diagram, is especially serious and often leads to worse verification scores. Apparently, the traditional scores are no longer appropriate for this detailed forecast. Because of the limitation in the traditional verification methods, a more complicated verification method is developed, which can better quantify detailed precipitation forecast. This method includes two major steps. First, the forecast and observations are transformed into fraction grids. Second, the fractions scale score is computed and used to evaluate the model performance. This figure shows a schematic example of fractional creation. If we look at one specific grid, for example, the grid denoted by the red cross, there is no precipitation in the forecast, but there is precipitation in the observation. We would say the forecast is wrong. If we look at the situation over the surrounding 9 grids, the forecast shows precipitation in 3 grids, but only 2 grids have precipitation based on observations. In this case, we would say precipitation is over forecast. When we consider the surrounding 25 points, forecast and observations have the same number of grids with precipitation. In this case, the forecast is considered to be correct. This is the basic idea for the new verification method. Based on this concept, a more detailed verification method has been proposed in recent years. The fractions Breyer score is calculated based on neighborhood grid fractions in the forecast and observations. Note that the objective verification only takes place over the specified area surrounding the grid of verification. NV is the number of grids that is used. The fraction Breyer score compares grid fractions between forecast and observations. The worst possible fraction Breyer score is the one when there is no overlap of non-zero fractions. Fractions skill score can be constructed based on the fraction Breyer score and the worst fraction Breyer score. Fraction Breyer score is negatively oriented. It is strongly dependent on the frequency of the event. Fraction skill score ranges from 0 to 1. As the number of grid boxes in the neighborhood increases, fractions skill score improves. This is an example of verification for WRF precipitation. We calculate traditional metrics of ETS and bias. We also calculate fractions skill score. Results indicate that the model performs better for simulation of light to medium precipitation, but not that well for heavy precipitation. Also, with the increase in the spatial scale, fractions skill score increases, indicating that verification results over larger area is always better than over small area. So I guess I will stop here. Please feel free to ask any questions. Thank you.